everyone, my name is Sophia Pedigo, and today we're going to be doing the final part of, I guess, kind of a collection of videos that I've been doing on finding the temperature profile for this bar of material that we have. So in my previous video, what we did is we found the Crank-Nicolson method for the temperature profile, and we were able to apply the von Neumann stability analysis to the Crank-Nicolson method, and we were able to determine that it is stable for like higher values of R. Because if you remember in the first version where I coded this, actually it's right over here, in this version, when we changed the values of R up here, I forget what it was. I think if we change, if it's this one, I think it gives us real, actually I'll probably have to start from here. It gives us real wonky graph because it's not stable. Let me see. Below. Yeah, obviously not what we would expect. That's not what's happening with the temperature profile of this. So we were able to apply the von Neumann stability analysis to a new equation that we're going to use, the Crank-Nicolson, and we'll be implementing that right now. So this is all very similar up until here basically. So most of this is just going to be copying and pasting. I've imported a couple things. I changed the length increments, and the time stays the same. So now I'm gonna import this stuff too, because that's all the same here too. And this we're gonna change to, I think that changes to 0.5. But if it's wrong, I'll know, or I'll check. And then we're going to say R is equal to, whoa, new line. And R we just define, if you remember my video. It's pretty much the same as the first one over here, except we're going to divide it by 2 this time. And that was because in the Crank-Nicolson, we're taking the average of the temperature profile at N, or at J, and the temperature profile no, it's N and then N plus 1, the different times. And we were taking the average of that, so we took the 2 out of our equation and defined it as part of this one. So we're dividing everything by 2. Yay. Okay, yeah, R is equal to 1. The first time I did this, I forgot to change the value of delta X. And then when I got to the end, everything was super weird. So don't do that. But next we're going to do our temperature array. And we're going to put zeros in it, so... No, not zeros. I'm sorry, I don't know why I said that. I was thinking of the next part, but ignore that. Did I already do that? I already did that, sorry. I'm really tired today, so I'm doing some crazy stuff. Yeah, sick. So yeah, this is, again, actually I probably just could have copied and pasted this now that I think about it. Actually, I will do that for these two, because now we're just changing the values for the first temperature and the final temperature. Yeah, so sick. It just changed that first one and then that last one. And so now that we've got our temperature array, we're going to move on to the next part of this. So up until now, everything's basically the same as when we did the first, not stability analysis, first temperature profile over here in this guy. But now we're going to be implementing the Crank-Nicolson method. So instead of using the equation that we used over here, let me fix that, sorry. instead of using the equation that we used over here for this part, we're going to be using the Crank-Nicolson. So to do that, we have to kind of create an array with diagonals, and we're going to solve those. So I'm going to do the first one here, and or not the first one, but like we're going to create the diagonals. And we're going to check and make sure. Yeah, so this is just our diagonals. I just filled them with 0. And then we're going to start, like, I guess you'd say populating the array. I don't really know. We're going to say that it's equal to -r. And this is just, yeah. So cool. It put in our values for -r, which I showed you the value of r was 1 up here. So -1. I'm going to kind of keep doing that for the different diagonals here. And this is just like based off of the Crank-Nicolson equation that we derived earlier. Yay. Yeah, so then this is just 2 times r, which would be 2, plus 1 is 3, and then putting that into the diagonals here. And then we'll do that for the last one too, or as well. I said 2, but then I thought maybe it sounds confusing if I'm like, am I talking about the letter 2 or the number, or not letter? Anyway, it's -1. And now we're going to do a similar thing for our next array. Never underestimate the power of making an array and just filling it with zeros, because I found that to be very helpful. Nice. And now we're going to start like implementing the equation, I guess. This is the best way I can just describe it. Sometimes I'm really bad at describing like mathematical things. Just cause it's almost easier to like see it instead of describing it. I don't know. But yeah, this is, you'll see what I'm doing. I'm just, words aren't my forte today, apparently. Okay, cool. So yeah, that just, same thing. Whoa, didn't mean to do that. Same thing where I think it was somewhere over here where we had an array. I think it was that guy. Similar concept here, except we're going to be, I mean, like it's a little bit different, but basically same concept of you have an array, you're populating it, and this time we're just doing it with the Crank-Nicolson, so it's a little bit different in terms of like the calculation that we're going to be doing. It's not exactly the same, but it's similar. And we're going to change the first value for b, that one. So it's going to be b 0 plus r times a t0. Cool. So 100. It basically just doubles it. And then we're going to do the same thing for the final, the last value. And this should just double it as well. Same concept. Oops. Yep, 116. All right. Now we're going to go ahead and kind of similar to how we had a subplot here, we're going to do that. So we say fig. It's going to have 1 row, 1 column, and we're going to do like our initial temperature basically. Oops. Look at that. Yeah, I think that's right. All right, so then we're going to do a for loop for our time increments, and we're going to like solve those diagonals. So okay. And then I'm literally just going to copy and paste this guy here. Because this is going to like solve our diagonals. Oops, I did not mean to do that. Curly brackets. Oh, if. My bad. I was trying to figure out why that wasn't working. Okay, cool. So that is our temperature profile based off of the Crank-Nicolson method, and based off of the stability analysis we did. This is going to be stable for any values of R. Um, so yeah, that's all I've got. That's kind of the end of this little session here. I'll see you next time then. Bye.